So yesterday we reviewed complex numbers on page 2 and part of page 3, example 5 on page 3 of your notes. Okay. And so next we're going to do example 6, where we have to solve quadratic equation in a single variable. Okay. Find all the values of x and make the left-hand side equal to 0. So I realize there isn't a lot of space there at the bottom underneath example 6, so you have to write small or use the space at the top of the page. So we have 3x squared minus 2x plus 5 is equal to 0. Now, if this could be factored with integers, right, we could certainly solve the problem that way. Okay? But we can't factor the quadratic on the left with integers. So we have to use a quadratic formula. And so a is equal to 3 in this case, b is equal to minus 2, c is equal to 5. And so the two values of x, which are the zeros, okay, of the left-hand side, the two values of x that make the left-hand side equal to 0 are given by the quadratic formula. Minus b plus or minus square root b squared minus 4 times a times c or 2 times a. Okay. And now we just plug in for a, b, and c, and then simplify to get the two solutions, the two values of x that make the left-hand side equal to 0. So negative b in this case is a negative of negative 2. And then under the square root, we have b squared, which is minus 2 squared, then minus 4 times a, which is 3, times c, which is 5. And then that's all over 2 times a, which is 2 times 3 in this case. Okay. And now it's arithmetic. Okay. So you got to use the order of operations and simplifying what's under the square root. Okay. So negative negative 2 is plus 2. And then under the square root, minus 2 squared is 4. Exponentiation for multiplication. Then minus 4 times 3 times 5 is minus 60. And then denominator 2 times 3 is 6. And so we know immediately now the solution to this quadratic equation in one variable is going to have complex numbers in the solution. Because 4 minus 60 is a negative 56. The square root of minus 56 is an imaginary number, not a real number. So what's under the square root is minus 56. And now we have to reduce the square root of minus 56, right? And so this is where you gotta ask yourselves, can I factor the number 56 where one of the factors is a perfect square? Okay. And in this case, the answer is yes. 56 can be written as 4 times 14. 4 is equal to 2 squared, right? You know, square root of 4 is 2. So this is equal to 2 plus or minus -1 times 4 times 14. So we're doing a little bit of review from yesterday here. Okay. Square root of -1 is I. Square root of 4 is 2. Square root of 14 can't be reduced. So this simplifies to 2I times the square root of 14. As a reminder, fraction bars are like division symbols. Division does not undo addition and subtraction, right? So each of those numbers in the numerator, each of those terms has to be divided by 6. Two 6 reduces to 1/3, and second fraction get the same thing, right? 2 and 6 are both divisible by 2. And we're left with I times the square root of 14 over 3. So the two solutions to this quadratic equation in one variable are x is equal to 1/3 plus I times the square root of 14 over 3, and x equals 1/3 minus I times the square root of 14 over 3. So these are the zeros of this quadratic equation. Those are the values of x to make the left-hand side equal to 0. But now we have to factor the left-hand side. Okay. And you know from the factor theorem at the top of page 1, okay, if x equals c is a 0 of a polynomial function and a quadratic is a polynomial of degree 2, okay, then x minus c is a factor of f of x. So we got to subtract everything on the right-hand side, move it to the left-hand side to get the factors. Okay. So we got to subtract 1/3 and I root 14 over 3 to get the first factor. So the first factor is x minus 1/3. Oh, while we're doing that, we're factoring 3x squared minus 2x plus 5. Right? That's what it means when I get the complete factorization. So the first factor, we subtract 1/3 from x, then subtract I root 14 over 3 from x. And the first factor is x minus 1/3 minus I root 14 over 3. And then to get the second factor, we subtract 1/3 from both sides and add I root 14 over 3. You have x minus 1/3 plus I root 14 over 3. This is the complete factorization of this quadratic 3x squared minus 2x plus 5. You know what? There's a small error. When we multiply x times x, if we were to expand this and multiply x times x, we get x squared. Our leading coefficient is 3. I forgot to multiply the right-hand side by 3. So it's 3 times x minus 1/3 minus I root 4/3 times the second factor. 3x squared minus 2x plus 5. If you were to expand the right-hand side when you multiplied these two factors, right? When you multiply first terms, you have x times x, which is x squared. But our leading term over here is 3x squared. So you have to multiply this by 3, the leading coefficient. So when you expand the right-hand side, you'll multiply 3 times x, which is 3x squared. I missed that one. So this is the complete factorization of this quadratic. It's not quite as nice as when you factor quadratics and the numbers are like +5 and -3. All right, so if you flip over to page, was it page 4? We have what is called the conjugate zeros theorem. Important theorem. Grab my highlighter. Let f of x be a polynomial function that has real coefficients, right? So there's an area of mathematics where we study polynomial functions that can have complex numbers for coefficients, but we're only dealing with real coefficients, right? So in this example here, right, the real coefficients are 3 minus 2 and plus 5, right? They're not complex numbers. If a plus bi is a complex zero of the function, then its conjugate a minus bi is also a zero of the function. So the conjugate zeros theorem says, right, when we're dealing with polynomial functions with real numbers for coefficients, the complex zeros come in pairs. If you know one complex zero, you automatically know the other complex zero. Okay? They come in pairs. They're conjugates of each other. So in example 7, we're going to find a polynomial of degree 5 that has integer coefficients, which are real numbers, okay, and zeros at x equals 1, x equals I, and x equals 2 plus I. Well, we're given the zeros are x equals 1, x equals I is the second zero. Now, this is I is a complex number of the form can be written as 0 plus I, right? 0 is the real part, and then plus 1 is the imaginary part. Okay. So the conjugate is 0 plus I is 0 minus I. So since complex zeros come in pairs, if x equals I is a 0 of the polynomial function, then x equals minus I is a 0 of the polynomial function. Okay. And then we're given x equals 2 plus I is a 0 of the polynomial function. So the conjugate of 2 plus I is 2 minus I. So those are the 5 zeros of our polynomial function. Okay. It says to find a polynomial of degree 5, right? So n equals 5, right, is the degree. And so we know there has to be 5 factors or 5 zeros to this polynomial function. And we just listed out the 5 zeros. Okay. So these are the zeros of our polynomial function. And now we can write out the factors. Right? From the factor theorem, if x equals 1 is a 0, then x minus 1 is a factor. If x equals I is a 0, then x minus I is a factor. And then x plus I has to be a factor. If x equals 2 plus I is a 0, then x minus 2 minus I has to be a factor. And similarly, x minus 2 plus I has to be a factor. So those are the factors of our fifth degree polynomial of degree 5. So, to find a polynomial of degree 5, right? It says find a polynomial of degree 5. Doesn't say anything about the leading coefficient. So we can just multiply the 5 factors to get a polynomial of degree 5. We have x minus 1 times x minus I times x plus I times x minus 2 minus I times x minus 2 plus I. So there's our factored polynomial. Of degree 5. And you can see if we were to expand this and multiply all the first terms, we have x times x times x times x times x, which is x to the 5th. Right? And so our leading term, right, would be x to the 5th, and the leading term determines the degree of the polynomial. So you can see the polynomial would be degree 5. Okay. All right. To show that, you know, we got, right, our factors, 4 of our factors contain complex numbers. To show that our factor, or if we expanded this polynomial, that it would have integer coefficients, I'm going to multiply these 2 factors and multiply these 2 factors. And you'll notice when we do that, the complex numbers go away and all we have are real numbers. Okay. So when I multiply x minus I times x plus I, and you can verify my math, okay, I got x squared plus 1. And at the bottom of, in example 4, at the bottom of page 2, I multiplied something like these 2 factors, right, 2 different ways, right? Said you can pick your medicine how you want to carry out that multiplication. And when I multiplied these 2 factors, I got x squared minus 4x plus 5. Okay. Now you can see there's not a complex number anywhere. So if we were to continue to expand this and write the polynomial in standard form, right, all the coefficients would be real numbers, okay? Because there's not a complex number anywhere. Okay. So we have all integer coefficients when expanded. We're not actually going to do that, right? You can do that on your own if you want, but you can see by foiling these 2 factors, multiplying out these 2 factors, the complex numbers went away and all we got are real numbers now, okay? Which meets the condition, okay, that has to have integer coefficients. All right. Any questions on that? So let's take a look at example 8. We're going to verify that x equals minus I is a 0 of the polynomial, and then find all other zeros. So we have f of x is equal to 4x to the fourth minus 8x cubed plus 9x squared minus 8x plus 5. And we have to verify that that x equals minus I is a 0. So let's just remind ourselves. I is equal to the square root of -1. I squared is equal to -1. I cubed is equal to -I. And I to the fourth is equal to +1, right? We did that on, what was it, page 2 yesterday. Okay. Well, in verifying that minus I is 0, this polynomial function, we have minus I to the fourth, minus I cubed, and minus I squared. Okay. So minus I squared, okay, we're squaring minus I, is equal to -1 times I squared, which is equal to -1 squared times I squared. -1 squared is 1, and I squared is equal to -1. So negative I squared is equal to -1. Okay. Minus I cubed, doing the same thing. Right? -1 times I cubed is equal to -1 cubed times I cubed. -1 cubed is -1, and I cubed is -I. So you have -1 times -I, which is equal to +I. So minus I cubed is equal to +I. And then minus I raised to the fourth power is -1 times I to the fourth power. It's -1 to the fourth times I to the fourth. -1 to the fourth is 1, and I to the fourth is 1. So minus I to the fourth is equal to +I. Okay. So to verify that this I, x equals minus I, is a 0, this polynomial function, put in minus I in for x, and then simplify. So we have 4 times minus I to the fourth, minus 8 times minus I cubed, plus 9 times minus I squared, minus 8 times minus I plus 5. And now you got to simplify. Minus I to the fourth is 1. So we have 4 times 1. Minus I cubed is I. So we have minus 8 times I. And then minus I squared is -1. So we have 9 times -1. And then minus 8 times minus I is plus 8I. And then plus 5. So this is equal to 4 minus 8I minus 9 plus 8I plus 5. Minus 8I plus 8I is 0. And 4 minus 9 is -5. -5 plus 9. So f of minus I is equal to 0. So x equals minus I is indeed the 0 of this polynomial function. Well, if x equals minus I is a 0, that polynomial function, then x equals plus I has to be, right? Because remember, complex zeros come in pairs. Okay? So if minus I is a 0, the complex of the polynomial function, then x equals plus I is 0. Okay? So these are two zeros of f of x. Okay? So that means x plus I and x minus I are two factors of f of x by the factor term. Okay. So we have a fourth degree polynomial. How many factors is that fourth degree polynomial going to have? From the, yeah, 4, right? Number of factors equals, right, the degree of the polynomial. But some of the factors can have, some of the zeros can have multiplicity greater than 1, right? Some of the factors may occur more than once. So, our fourth degree polynomial here, okay, can be written as x plus I times x minus I times some unknown quadratic, okay? So this fourth degree polynomial, we got two linear polynomials as factors, so q of x has to be a quadratic. Okay. Well, when you multiply x plus I times x minus I, you get x squared plus 1. So this fourth degree polynomial is equal to x squared plus 1 times some unknown q of x. Okay. So to find the other remaining two zeros of this polynomial function, we got to figure out what q of x is. Well, q of x, if I divide both sides by x squared plus 1, q of x is equal to 4x to the 4th minus 8x cubed plus 9x squared minus 8x plus 5 divided by x squared plus 1. Okay. Can we use synthetic division to do that division? The answer is no, because that's not linear in the denominator. That's x squared. So what kind of division do we have to use? Long division, right? So we got to divide x squared plus 1 into 4x to the 4th minus 8x cubed plus 9x squared minus 8x plus 5. This is always good review, right? Because this is I tell you right now, you're going to do long division on the quiz on Friday. Okay. So, right, you got to remember this is the called the dividend under the square root. It's going to be written in descending powers of x. This is called the divisor. It's going to be written in descending powers of x. And so first you got to ask yourself is how many times is x squared going to 4x to the 4th? 4x to the 4th divided by x squared, which is equal to 4x squared. So x squared goes into 4x to the 4th, 4x squared times. And then you got to multiply 4x squared times the divisor. And when you distribute, you get 4x to the 4th plus 4x squared. And you're going to subtract that 4x to the 4th plus 4x squared from the dividends. And then when you distribute the minus sign inside parentheses, plus 4x to the 4th becomes minus 4x to the 4th plus 4x to the 4th is 0. If what's in the first column doesn't go away, you did something wrong. And then there's no x cubed term, so we have minus 8x cubed minus 0, which is minus 8x cubed. And then plus 4x squared becomes minus 4x squared. And minus 4 plus 9 is plus 5. We have plus 5. And then we bring down the minus 8x plus 5. And now we got to ask ourselves, how many times does x squared go into minus 8x cubed? Well, minus 8x cubed divided by x squared is equal to minus 8x. And then we got to multiply minus 8x times the divisor, x squared plus 1. Then when we distribute the minus 8x, we get minus 8x cubed minus 8x. So that's going to get subtracted from our new dividend. Now when you distribute the minus sign, minus 8x cubed is plus 8x cubed, plus 8 minus 8 is 0. Minus 8x becomes plus 8x. Oops, I should have wrote that over here. Sorry, guys. Wrong column. There's no x squared term. Okay. So minus 8x cubed minus 8x. We're subtracting that from up above. So minus 8x cubed plus 8x cubed is 0. Then we have 5x squared minus 0, which is 5x squared. And then this minus 8x becomes plus 8x, plus 8x minus 8x is 0. So we're just left with 5x squared. Unless I made a mistake. Which appears I have not. So now we bring down the plus 5. And now you can see x squared goes into 5x squared 5 times, right? 5x squared divided x squared is plus 5. And then we multiply x squared plus 1 by 5, and we have 5x squared plus 5. And that gives us a remainder of 0. We're subtracting 5x squared plus 5 from 5x squared plus 5. Does that surprise you? The answer is no, because x plus I and x minus I are factors of this polynomial, right? X equals minus I and x equals I are zeros of this polynomial. So since they're zeros of this polynomial, we better get a remainder of 0. All right, so Q of x over here is equal to 4x squared minus 8x plus 5, right? So we find the values of x that make this equal to 0, and then we'll have the remaining 2 zeros of our polynomial and the remaining 2 factors. Okay. So we have to find the 2 zeros of this quadratic. We have to set it equal to 0 and solve for x. Well, a is equal to 4, b is equal to negative 8, c is equal to 5. the quadratic formula, right? X is equal to negative b, which is negative of negative 8, plus or minus the square root of b squared, which is minus 8 squared, minus 4 times a, which is 4, times c, which is 5, divided by 2 times a, which is 2 times 4. Well, negative of negative 8 is plus 8. Minus 8 squared is 64. And minus 4 times 5 is minus 8. All divided by 8. Well, 64 minus 80 is negative 16. What's the square root of 16? 4. So this simplifies to 4i. So x is equal to 8 plus 4i divided by 8. And again, division does not, oops, this should be plus or minus, sorry. There are two solutions. Again, division does not undo addition and subtraction. So we have 8 over 8 plus or minus 4i over 8. So our two additional roots, or additional zeros of our fourth degree polynomial function are x equals 1 plus or minus 1/2 i. So x equals 1 plus 1/2 i and x equals 1 minus 1/2 i are the two remaining zeros of f of x. So the complete factorization of f of x is equal to x plus I times x minus I. Times x minus 1 minus 1/2 I times x minus 1 plus 1/2 I. That's the complete factorization. Once you know the zeros, you can write out the factors. Okay. Any questions on that problem? So all polynomials can be factored, but most of them are probably going to have complex numbers when you do the factor. Okay. All right. Example 9. I do believe we're going to get through this. do tonight. Since we finished it today. No. That'd probably be considered cruel and unusual punishment. Alright, example 9. Again, it looks like we're dealing with a 4th degree polynomial. One solution to the equation, x to the 4th, blah, 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 equal to 0, is the complex number x equals 1 plus 2i. Determine all the solutions to this equation. Okay. So how many values of x make the left-hand side equal to 0? How many solutions are there to this equation? 4, right? Now, it is possible that one or more solutions may occur more than once, okay, because of multiplicity, okay. But, right, it's a 4th degree polynomial, okay, so we're expecting 4 solutions. 4, the left-hand side can be factored, right, into 4 factors. All right. So the degree, the polynomial on the left is equal to 4. So we're expecting there to be 4 zeros, right? 4 values of x to make the left-hand side equal to 0. Now we're given x equals 1 plus 2i is 1 0 of the left-hand side. So what's another 0 of the left-hand side? 1 minus 2i. Remember, complex zeros come in pairs. So x equals 1 plus 2i, and x equals 1 minus 2i, right, are zeros. Those are 2 solutions to our 4th degree polynomial equal to 0. Okay. So the corresponding factors are x minus 1 minus 2i and x minus 1 plus 2i are 2 factors of our 4th degree polynomial. So x to the 4th minus 6x cubed plus 14x squared minus 22x plus 5 is equal to this factor times this factor times an unknown quadratic called q of x. And it has to be a quadratic, right, x squared, because our polynomial is a 4th degree polynomial. X squared times x gives us x to the 4th. Okay. All right. So let's expand x minus 1 minus 2i times x minus 1 plus 2i. And I think it was at the bottom of page 2. Okay. We did a similar expansion, except it was minus 3 instead of minus 1. Okay. So you can review that. Remember, again, there are 2 different ways to multiply these 2 factors out. You pick the one that works for you. Okay. And so when I multiplied out these 2 factors, I ended up with x squared minus 2x plus 5. And that's times the unknown q of x. So you might want to leave some space. I'm going to add a couple lines down here. But again, how do we find q of x? We got to divide, right? If we divide both sides by this quadratic, we'll end up with q of x by itself on the right hand side. So we'll have 4th degree polynomial divided by a quadratic. And again, you got to do long division. Okay. So x squared minus 2x plus 5. Now I'm going to speed up the long division, right? We've done this several times. So we're dividing x to the 4th minus 6x cubed plus 14x squared minus 22x plus 5. X squared goes into x to the 4th, x squared times. And when you multiply the divisor by x squared, you get x to the 4th minus 2x cubed plus 5x squared. And when you subtract this in parentheses from the dividend, you end up with minus 4x cubed plus 9x squared. And then you got to bring down the minus 22x plus 5. Then you got to ask yourself, how many times is x squared going to minus 4x cubed? Well, minus 4x cubed divided by x squared is minus 4x. So now you multiply minus 4x times the divisor, and you get minus 4x cubed plus 8x squared minus 20x. And that has to be subtracted from the dividend immediately above it. And when I did that, I got x squared minus 2x, and then we bring down the plus 5. And you ask yourself, how many times is x squared going to x squared? X squared divided by x squared is plus 1. So plus 1 goes up here. Plus 1 times the divisor is x squared minus 2x plus 5. And when you subtract that from itself, you get 0 for the remainder. Which you should, because x, right? These two guys are factors of our 4th degree polynomial. Okay. So our 4th degree polynomial is equal to x squared minus 2x plus 5 times the quotient from our long division, x squared minus 4x plus 1. So to find the last two zeros of our polynomial from our 4th degree polynomial equation, we got to set this quadratic equal to 0 in parentheses and solve for x. Okay. We basically did that in the previous example. Okay. So x squared minus 4x plus 1, right? We set that second factor, that second quadratic, equal to 0. Solve for x. So a is equal to 1, b is equal to minus 4, and c is equal to plus 1. Is anybody still copying down the long division? So x, right, is equal to negative b. So we have negative of negative 4 plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a, 2 times 1. Now it's arithmetic. Negative 4 is plus 4. And what's under the radical square root? Minus 4 squared is 16. So we have 16 minus 4, all divided by 2. 16 minus 4 is 12. So the values of x that make the left hand, that make this quadratic equal to 0 are not complex numbers. (16 minus 4 is 12, but 12 is equal to 4 times 3. The square root of 4 is 2, so this radical reduces to 2 times the square root of 3. So this is equal to 4 over 2 plus 2 root 3 over 2. And so the two values of x that make this quadratic equal to 0 are x equals 2 plus the square root of 3 and 2 minus the square root of 3. So x equals 2 plus the square root of 3 and x equals 2 minus the square root of 3 are the two remaining solutions. Or zeros. That's interesting. Because when we have integer coefficients in our polynomial, these are not rational numbers, these are irrational numbers, right? Square root of 3 is an irrational number. So solutions with irrational numbers also come in pairs. Plus root 3 minus root 3, okay? As long as you got integer coefficients. And so the complete factorization of our 4th degree polynomial, x to the 4th minus 6x cubed plus 14x squared minus 22x plus 5. The complete factorization, the first two factors, right, are with have the complex numbers. We have x minus 1 minus 2y times x minus 1 plus 2y. Those are the first two factors. And then the second two factors have the irrational numbers. So you do the same thing, right? You gotta subtract 2 and root 3 from x. We have x minus 2 minus root 3. And then over here, right, we gotta subtract 2 and add root 3. We have x minus 2 plus root 3. So this is the complete factorization. Of that 4th degree polynomial. Okay. Two of the factors contain complex numbers, and two of the factors contain irrational numbers. Any questions on that, ladies and gentlemen? Okay. Last one, example 10. Verify that x equals 1/3 and x equals 3/2 are zeros of the polynomial function. Find all other zeros and give the complete factorization of f of x. So again, it's a 4th degree polynomial. So we're expecting 4 zeros, and we're given 2 of them. So we got to find the remaining 2. What do we go to? Is it 1050 that we go to? My bad. Okay. All right. So we got f of x is equal to 6x to the 4th minus 5x cubed minus 2x squared minus 8x plus 3. And so to verify that 1/3 is x equals 1/3 is a 0, right? You evaluate the function at x equals 1/3. So we have 6 times 1/3 to the 4th minus 5 times 1/3 cubed minus 2 times 1/3 squared minus 8 times 1/3 plus 3. And when you do that arithmetic, you get 0. Okay, now I'll leave you guys, that's PEMDAS working with fractions. Okay. I'll leave it to you to verify. Okay. And similarly, to verify that x equals 3/2 is a 0, you evaluate the function f of x at x equals 3/2, and you'll see that the right hand side equals 0. Okay. So I'm gonna leave that. You can do that on your own. Okay. If you have difficulty, let me know. We'll go over it together. All right. Find all other zeros and give the complete factorization f of x. Now this is one case where we can use synthetic division. Okay. Because x minus 1/3 and x minus 3/2 are factors, linear factors, okay? And so we can divide this 4th degree polynomial by x minus 1/3, and then take the result of that division and divide it by x minus 3/2, okay? And so we're going to divide f of x, 6x to the 4th minus 5x cubed minus 2x squared minus 8x plus 3 by the first linear factor, x minus 1/3. Okay. And that will give us a quotient. And then we take that quotient and divide it by x minus 3/2. Okay. And that will give us the quadratic that we're missing. So c is equal to 1/3 in this case. So 1/3 goes in the box. And then you write out the coefficients to the right for 4th degree polynomial. 6 minus 5 minus 2 minus 8 and 3. And now you do the synthetic division. Bring down the 6. Multiply by 1/3, you get 2. Minus 5 plus 2 is -3. -3 times 1/3 is -1. Negative 2 plus negative 1 is negative 3. Negative 3 times 1/3 is negative 1. Minus 8 minus 1 is negative 9. And 1/3 of minus 9 is negative 3. And 3 minus 3 is 0, which is the remainder, which is what you better get. Okay. So minus 9 in the quotient of this division, minus 9 goes with 1, gets multiplied by 1. Minus 3 gets multiplied by x. Minus 3 gets multiplied by x squared. And 6 gets multiplied by x cubed. So the quotient from our division is 6x cubed minus 3x squared minus 3x minus 9. Okay. Are you with me? Now we're going to take this third degree polynomial and divide it by x minus 3x. So, right, so C is equal to 3/2. So 3/2 goes in the box. And then the coefficients of our third degree polynomial are 6 minus 3 minus 3 minus 9. Now we do the synthetic division. Bring down the 6. 6 times 3/2 is 9. Minus 3 plus 9 is 6. 6 times 3/2 is 9 again. Minus 3 plus 9 is 6 again. 6 times 3/2 is 9 again. Minus 9 plus 9 is 0. So we get the scary number 666. Okay. And so this last 6 goes with 1. The middle 6 goes with x. The first 6 goes with x squared. So this third degree polynomial divided by x minus 3/2 is equal to 6x squared plus 6x plus 1. So to get the last two zeros now, we got to set 6x squared plus 6x plus 1 equal to 0 and solve for x, right? Oop. That shouldn't be plus 1, that should be plus 6, right? And since each of those coefficients is 6, you can factor out a 6 or divide both sides by 6 and solve the equation x squared plus x plus 1 is equal to 0. We don't have time, so we will do this last little bit first thing tomorrow, but you should be able to do this on your own, right? Get the last 6 zeros, okay? So I'll see you tomorrow. Have a good day.